Okay, so just so everyone knows, I'm recording. Let me make an announcement. All right. So what I need you to do is at least one person or whoever wants to do it from each company, if you're in the group one options that is doing the company simulation, is to go into this checklist and modify the dates. I did put in the checklist and highlighted in, oh, it didn't transfer. I think if you open it in Excel in Word, you'll see yellow highlighting. So I put yellow highlighting in to show where that changes occurred. And it's not going to go there, is it? Okay, well, it doesn't want to move on me. That's fine. Let me go back to the announcement. Okay. Then I made a video that goes over how I did some of the things in the technical report, which was basically formatting tables or just some like tips and tricks on how to use Excel to do that. So I made a video for that. And also what are all the variables that we're going to need as part of the assignment that's due tonight. So I do a video where I go over a lot of those details. All that is in this one video. Well, it's in this assignment. If you go to this assignment, at the, I think some people might have missed this, that in the assignment, oh, sorry, it's not going to show it to me the way you see it, unless it takes me a long time for this thing to load. Let me see if I can just get it to view it like this. Okay, so when you go through the directions on doing the analysis plan 2, they're sort of repeat of analysis plan 1. They just talk you through doing it, your original work, grading it, and then doing the final corrected version. But what I wanted to make sure you notice is if you scroll to the bottom, there's a class example task 1. And those are sort of like notes that you would take if you had a meeting with the client and were going to, keep track of what you were going to do. So the template you can use for any assignment, you could use a template for any future work, any analytical work. This is specific to Catherine Hill and her class project. So this is where we've kind of had meetings, they're notes from me, but theoretically in our simulation, they came from meetings that we had where we wrote down how we were going to do this and kind of talked about it. So the video goes through more granular description of all this. Okay, so that's what's going on with that. Any questions so far on that part? I'm going to switch over to the weekly to-do list, which I should have put at the top. Let me open that up. Okay. So can you guys still see my screen? I'm not seeing you can. Okay, good. All right. So everyone needs to read the chapter 3 SMART book. That's due Sunday night. And that's going to be a big time review for the most part. There's a few things in there that might be a little bit new, but it's very much a review in some sense of all the stats you learned prior to my class or should have learned. So, and then there's an optional chapters 3 and 4 Excel. So that's a nice one to kind of keep working on your Excel skills. Then if you're in the back group, I try to kind of write out granular, all the things that were due between now and next Monday. So there's the writing of the analysis plan 2, finishing up the technical report corrections, grading your colleagues' analysis plan 2, part 2, sorry, task 1, part 2, and then correcting your own, and then actually doing the work in Excel. Okay. And then if you're in the exam group, if you made an 89.95, if you made under an 89.95, then you need to complete the exam 1 autopsy assignment, which is due on Thursday, March 9th. And here's the link to that assignment. You're basically going to go into Connect and write a sentence with explaining what the right answer is for each one you got wrong. And also on the classwork, I will be handing those back out on Thursday for whatever you need to correct from that work. And then there's the optional exam prep on chapter 3, where you have some problems. That's going to review a lot of how do you take an average, how do you take a median, mode, things like that. That's what we're going to be getting into. Okay.
The week six to-do list is not popping up on my Brightspace.
Interesting. Oh, thank you. I have to make it visible. I appreciate you telling me that. All right, it should be visible if you refresh your browser. Okay. Given all that, then let me go ahead and get going on what we're going to cover today. So I'm going to start today. We're going to talk about, I'm going to maybe make this a little bigger. Well, I guess I don't have to. Is this large enough for everybody? I can zoom this in a little, maybe. It might be a little bit too much. All right. So I'm going to be talking today about chapter 3. And this is basically summary measures. So the idea here, and I'll just try and maybe do some bullets the way I do in class, is that we can use numerical descriptive measures to extract meaningful information from data. All right, so that's kind of like a big blanket statement about summary measures. These measures provide precise, objectively determined, in other words, there's no opinions here, values that are easy to calculate, interpret, and compare with one another. Okay, so we're going to talk about basically 4 different categories of these in chapter 3. And like I said, most of these will be a review. The first one is central location. So this is a typical or central value in the data. The next category is dispersion. This is really important. I know that probably up till now in your life, you've cared a lot more about average values. And while they still are important, when it comes to analytics, what ends up really mattering is the dispersion. Because if your data is really dispersed, and I go back again to the static on the radio signal, it's like you can't really hear the signal if there is one there as well. So these measures become really like important to us. We want them we want our data tight. So this is the variability in the data. Okay, then we're going to talk about shape, and this is whether or not the distribution is symmetric. That's probably the most important consideration for what we're doing. Certainly, there's other aspects to the shape of a distribution that can matter in other contexts. And then the big one for our 211 course is association. And we're going to start basically looking at correlation, which you may have heard of. Those of you who've had a statistics class that was not BAI211, you probably did cover correlation. It's currently not part of what we cover in 210. And if you took 210 at URI, you know there's a lot of material in 210. So it's really hard to add more there. So that's part of the reason we don't cover it. But we're going to cover it, and it's going to become sort of the backdrop for the regression analysis, which is as I told you, really important for our course. So association, whether two numerical variables have a linear, so this is where we're starting this whole journey down this path of looking for association, looking for trends, trying to see if we can find what we're going to end up calling predictors. Okay. So given that is sort of where we're starting, we're going to start with section 3.1, which is measures of location. And we're going to talk about measures of location in general, but we're going to start with talking about the big three for central location. So I guess let me go back to my bulleting here. So central location. So the first one, which I'm sure you're aware of, is the primary one, is the arithmetic mean. Is the primary measure of central location. And it's referred to as both the mean or the average, right? So these are not different things. So if you've ever kind of had that little concern, are they a little different? No, those are synonyms. And as we know, we're going to simply add up the observation, simply add up the values of all the observations and divide by the number of observations. I think I have my little, my goodness. Hold on one second, guys. I'm trying to get something open over here. Zoom just like really takes over. All right. Here we go. So when we talk about an average or central location, we can talk about it in terms of a population or a sample, right? So here, the sample mean, if it's a sample, is denoted with X bar. And suppose you have n observations in the sample, X1 through Xn, then the notation, remember the summation notation, and I can maybe make that just a little bit bigger. It's just, we're going to add up all those values, divide by n. So this is the math that is just a repeat of the bullet above. And if you recall, if we have a population or of many, many values, a sample would be just a subset of that, a random selection. And so each sample is going to have its own sample mean, whereas the population has a population mean. Yes. So the population mean is the same formula. The only thing is you have access to all the values in that population. And that's the one that we give the notation mu to. And I probably, just to keep things kind of organized, should indent this part right here, and we'll come down here. We're going to talk here about the median. All right, so the median is the middle observation. So half of the observations fall below and above the median. So this implies that the data has been ordered. So we're going to order our data. And let me go ahead and do that. A little formatting. All right. Note, right, you guys may remember this, right? That the median could be halfway between the two middle values if the sample size is even. And it is also called the 50th percentile, which we talked about that already. And we also talked last week about it being the second quartile. One of the things about the median is it is robust against outliers. And again, we have gone through this whole data cleaning. You guys should know this like the back of your hand by now, that the median is robust. That means the value won't change. Let's say the median is a robust measure. Of central location. So it's not influenced by outliers. And this is part of the reason we use that guidance when we decide what we're going to impute, right? All right. And finally, we have the mode. Is the most frequent. If all the values occur only once, there is no mode. Okay. There can also be ties. On what's the most frequent, and hence more than one mode. In Excel, so you guys have seen the average function, right? So maybe we should come up here, just if, not that we really need this because you guys should know this already, but in Excel, the function that we use is average. And then we put in a range of data. And for the median, we already know this one too. It's median, and then we put in the range of data. So in Excel, this one we haven't done. It's called mode molt. And basically what it does is it's going to create a little column of all the modes. So if there's more than one, it will overwrite anything below where if you need, like, let's say there's 3 modes, you have to have enough space in Excel to have 3 rows, right? I mean, 3 values. So you have to be careful. So make sure there's vertical room below the location of this function in case there are multiple modes. So then we have, so that's central location. So we're talking about measures of location. The other big topic are percentiles. So we started to talk about this when we were talking about binning, and we were talking about binning the same numbers in each bin, right? And so I gave you a review already on percentiles. So let's just put it here for completeness sakes, is a percentile. I'm not going to reteach what I already taught last week, but which was already a review of earlier statistics courses. But a percentile is technically a measure of location, right? However, it is also a measure of relative position. Okay. So let me scroll up a little bit here. Maybe. No. So the pth percentile divides the values of a variable into two parts. So I just lost my bulleting. So what I'm doing is I'm going back to the previous bullet, hitting return, and then hitting tab here so that I get the bulleting structure in Word kicking back on in a way. Okay, so that's just, again, a Word thing. Approximately P% of the values are less than the P percentile. And approximately 100 minus P. So if it's 25, it's 25th percentile, 100 minus 25 is 75. So the 75% of the observations are greater than the P percentile. All right, so that we know this. And I already reminded you that the value where this happens is the quantile. So we also have some popular quantiles, which we already reviewed last week. So this is already in your notes again. So you can refer back to that where we talked about quartiles, quintiles, deciles. And if you recall, in Excel, oops. So notice that this wants to pop this underneath here where it's not where I want it. So I'm going to select the data that I want to have at a higher level in the bulleting hierarchy, and I'm going to go up here to decrease indent. Okay. So Excel, recall, I said to use percentile dot inclusive, and then you would put the data, and then you add the percentile that you want as a decimal. And what I told you was that the .inc includes the minimum and the maximum, the 0 and the 1. And there is a little controversy in the world of statistics, and there's some statisticians that don't think you should include the minimum and the maximum. And so Excel has the alternate function, the percentile.exe, which excludes the minimum and the maximum. By far, the vast majority of statisticians believe you should include it for all practical purposes. There are theoretical reasons why the other way makes sense, but since we don't care about the theory so much in our class, we want to use this as a tool for business decision making. So we are definitely sticking with this one. Okay. So we can also, when it comes to percentiles, talk about summary measures. And this is where we talk about the 5-number summary, which again, we've talked about multiple times in our class. So this is the minimum, Q1, Q2, or the median, and then Q3, and then the maximum. And we can visualize this with a box plot, which we've talked about extensively. Okay. So I do want to point your attention to that some of these, actually, I'm going to come back to that. Let me make a note. Hold on 1 second. The next thing I want to talk about is section 3.2, which is measures of dispersion. Shape, and association. So let's start talking about, first of all, measures of dispersion. This part, again, should be very much a review for you. That doesn't mean that right off the bat you remember everything. It's just when I say it and go over it, you're like, oh, yeah, I remember that. Okay, so let's talk about that. Measures of dispersion. So these measures gauge the variability. I think I spelled that wrong. Okay, sorry. So usually 0 indicates all the observations are identical. So the measures of dispersion, just to be clear, usually indicate the smaller the number, the less variability you have. So these increase as the observations become more diverse. So let's talk about some of these measures. So the range is the one we're going to start with. This is the simplest. Of all the measures of dispersion. And it's just the difference between the maximum and the minimum. one of the problems, besides that it has very little information, but it does not tell you, it's basically going to be very strongly affected by outliers. So it doesn't really tell you about what's going on in the middle. It focuses solely on extreme observations. Right. The next one that is related to it is the interquartile range. So I probably should write it out for your notes. Which we have talked about extensively, use this a lot. Okay. So this is the difference between the third quartile and the first quartile. It's the range of the middle 50% of the data values. And what's great about that is it kind of gets rid of the problem of the outliers, the extreme values, changing your understanding. It gives you really like, where's the middle of my data? How wide is that range? And that is much more valuable to know. Not as influenced by extreme values. Right, then there's another one that's called the mean absolute deviation. Also referred to as the MAD. So it's going to be the average of the absolute differences between the observations and the mean. So I'm going to copy over the formula. I have a, if anybody's interested in learning how to type math formulas in directly to any work, I have a little PDF document. So just email me if you're interested in that. I might actually be able to put it on Brightspace too. And it just kind of talks you through how you create this kind of stuff without it being that much work. Okay. All right, so far, hopefully all of this is sounding very familiar. Maybe this mean absolute deviation is the new one for you, just to draw your attention to that this is the absolute value. So you take and you get the absolute value of every value in your data. You subtract how far away is it from the average in your data. And you don't care if it's above or below the average. So we take the absolute value, we just get the distance. And then we add those up and divide by the total. So that's how we get that mean absolute deviation. Right. So then we get to the variance and the standard deviation, which are two of the most common ones. So the variance and the standard deviation are the two most widely used measures of dispersion. And really one's just a square root of the other one, right? And it's sort of related to this mean absolute deviation, except that the values are squared. So the idea is you're going to compute the average of the squared differences from the mean. And the reason for that is that the squaring of the differences, unlike the one above it that's just looking at the absolute value, by squaring them, you're going to emphasize larger differences. So it just kind of, the value is a little bit inflated due to outliers, if you will. So it enables you to see that. And that is, there's a whole bunch of statistical theory why that is important and where all that comes from. So the population variance is denoted by, so this is that stuff that I was saying I can share with you if you are interested in how I do this. Sigma squared and the population standard deviation is denoted just by sigma. Now, the reason we always end up kind of looking at the sigma instead of the sigma squared is because the units of the standard deviation match the units in our data, whereas the units of the variance match are going to be whatever it is squared. So I'm going to write these formulas in here for you. So you take the difference from the mean and you square it, and you take the average over that. And once you have that variance, you just take the square root of it, and that's how you get the standard deviation. Okay. And similarly, so I'm just going to copy this all down and change certain things, right? So let's copy. So the sample variance is denoted by S squared, and the and the sample standard deviation is denoted just by S. Okay, so the formula for the S squared is going to be the difference from, it's no longer from this mu, it's now from the sample mean. So this is the X bar, and it's no longer divided by the population size. it's now divided by n, the sample size minus 1. Okay, but once you've done that, then the standard deviation, which is just S, is going to then just be the square root of the sample variance. Okay. All right. Then we have one that actually may be new to you. I don't think I talked about it in my 210 class, but it's something that we use a lot, actually, quote, in the real world. And that is the coefficient of variation. So the last one where we're talking about measures of dispersion is the coefficient of variation. Commonly referred to as the CV. So this is a relative, measure of the dispersion in relation to the size of the mean. So CV is, for a sample, is given as the sample standard deviation divided by the sample mean. So same formula, if it's population, we just change the sample standard deviation to the population standard deviation, or sigma, divided by the population mean, or mu. Now, the reason why this ends up being important to us is it's going to enable comparisons of the amount of variability from different data with different means. So let me just go give you an example about that one. Consider that GPA for some group had a population, let's say for this, I don't know, entering freshmen after high school GPA of entering freshmen. And it's determined to be equal to 3.5 and have a standard deviation equal to 0.6. And then we want to compare that with their SAT scores. And let's say their SAT scores their average of the entering freshman is 1050. And their standard deviation was 86. Okay, so the question is that the coefficient of variation answers or helps us with is, well, which of these two measures is more variable? in the population, right? Which is more variable? Well, what we would do to answer that question is we would calculate the coefficient of variation. And so for the first one, I'm going to do it for the GPA. And I'm going to say, well, that's just the amount that the 0.6 is out of the 3.5. And that on my calculator comes out to 0.1714. And I want to compare that variation. So that's saying that my standard deviation in this population, the standard deviation represents like 17% of the mean. And then what we want to do is compare that with the SAT measure. Oops. Sorry. And that has a standard deviation of 86 and a mean of 1050. So if we put that in our calculator, we get that this is 0.0819. So from here, we can see that since, oops, nope, I don't want to go back to equation mode. Sorry, sometimes Word thinks it's being helpful and it's not. All right, it's going to give me trouble now, but that's okay. Since oh, geez, come on. Sorry, I'm having a little lag between my keyboard and what you're seeing, what's showing up. Okay, since, right, the 0.01714 is greater than the 0.0819, the values of GPA are more variable than the values of SAT scores. All right. So what I'd like you to do is put your name in the chat again, please. Just want to make sure you're here, still with me. Okay. So now I'm going to get into a little bit of some new material, well, maybe some new material. It's not really new, but it's stuff you've kind of thought about or talked about indirectly. So let me see if I can get my Word to let me come in here and actually. So we talked about measures of dispersion. And now I'm going to talk about measures of shape. So one of the things that Word does is it gets kind of it gets itself in a knot, if you will, with this indentations and the bullets. So what I find is the easiest workaround rather than trying to fight with it is to go up to my highest point where I'm at right now and hit return. And here I'm going to measures. If you're doing Word, this is how you do it. If you're just taking notes, don't worry about this part. So then I'm going to take everything below it and I'm going to cut it, come back up here and paste it in. And that way I can now have my measures of shape bulleting in Word, go back to what I want it to be. Okay, so measures of shape. Okay. So we're going to talk about two measures of shape. We're going to talk about skewness And we're going to talk about kurtosis. So skewness, you already know about a distribution being right skewed or left skewed. So when it comes to skewness, we're going to talk about, actually, I'm going to back up a little here. I'm going to say the skewness coefficient. So this gives a number to the amount of skewness. So first of all, skewness, oops, I don't want that. Skewness for a symmetric distribution is assigned 0. So this is also by default, not all symmetric distributions are normal, but all normal distributions are symmetric, right? So this means this is true for normal distributions. Okay. Then if it's positively skewed, has a positive skewness coefficient. And a negatively skewed distribution has a negative skewness coefficient. The numbers themselves don't mean that much. Recall, let me see if I can get this to draw for me decently. Start with black. If it's positively skewed, you're going to have a distribution that has a right tail. Okay, so this is the positively skewed. And if it's negatively skewed, the tail points to the left. And the hump is over to the right. So the tail points in the direction of the skewness. That's supposed to be an arrow. Okay. In Excel, the way to get the skewness coefficient is using the function skew, and then you put in your data range. Okay. And you do not need to know this, so let's put that first. But in case you're curious, I know you're just dying to see this. I'm going to put the formula for what the skewness coefficient looks like. All right, so it's involving the sample size, the difference from the mean the difference from the mean divided by the standard deviation and that quantity cubed. So that's what's going on with that skewness coefficient. So that gives you a measure of that. And then we're going to talk about kurtosis. So let's understand what kurtosis is a little bit. So recall that some distributions. Oh, and before I forget to tell you, I did put 2 videos on our Brightspace page under the exam 2 content that also talks about skewness and kurtosis from a different professor's perspective. So in case you want to hear it again from someone else. Okay. So recall that some distributions have fatter tails. Okay. So that just means there's more data in the tails. So recall, for example, the T distribution is one of them. And then also, you can also have some have thinner tails. Okay, so there's less data in the tails. Well, it turns out that mathematically to be true, it is possible for data to have the same mean, the same standard deviation, and the same skewness, but have different shapes. Hence the need for the kurtosis. So if you're trying to figure out like, how do you other than doing a drawing or a graph of your data, how do you describe it so you can actually tell the difference? So it turns out you think, okay, if you have the average and the standard deviation, well, it turns out you could have data has very different distributions. But then if you think about skewness, you think now you've kind of narrowed it down, but it turns out that's not enough. And this is where kurtosis adds the more information so that you're really able to decide if 2 distributions are similar or different. So kurtosis is usually the deciding factor in these cases. Okay. So let me, first of all, give you a little picture of one, of what this looks like. Let's see if I can grab this image. Okay, so here's an example of 3 curves. They all have the same amount of mean, they all have the same mean, and they all have the same standard deviation, and they all have the same skewness. What's different between these is the kurtosis. So if you notice the kind of in the middle, you'll see a red curve. That's a normal distribution, and its kurtosis is given as a 3. So a normal distribution will always have a kurtosis of 3. The blue higher peaked one has a kurtosis of 4. And the green kind of squashed one, if you will, has a kurtosis of 2.7. Okay. So, in some sense, the number is reversed, right? So the kurtosis value that was lower refers to kind of a fatter middle area. But actually, because these have the same mean and the same standard deviation, it's not totally obvious in this picture, but the blue one has outliers. So in order to have the same mean and same standard deviation, it has more data out here in the tail and more in the middle, but less, sorry, more right at the peak, but in what's called the shoulder region. Let me draw the shoulder region for you. So the shoulder regions how to move some of that area out. So a little bit of theory for you. Don't worry about it if you're not totally getting that. I just want to give you an idea that there's this other measure of shape. Okay. So the kurtosis, oops. Gives a number to the amount of fatness or thick, how high above the x-axis it is, or thinness of the tails. And it does this by providing a number that can be compared to the size of the peak. The kurtosis coefficient can range from 1 to infinity and is 3 for a normal distribution. Because of this, often what is calculated, so there's a little bit of confusion. Technically, everything I told you so far is correct, but there's a little bit of confusion because often what is calculated is the excess kurtosis. Or EK, and that's the kurtosis minus 3. So it's just the difference from the normal. This is the value given by Excel as kurtosis, but it's really the excess kurtosis. So to emphasize it again, for a normal distribution, Excel will say kurtosis is 0. But Excel is actually providing excess kurtosis. So Excel's kurtosis which is really EK, right, or the excess, will, as a result, range from -2 to infinity. So a little counterintuitive, but compared to my normal distribution, with the same mean and standard deviation, if the data, oops, has outliers, the tails, this is what I was just talking to you about, the shoulder thing, will be fatter. Because that means that there's actually data out in the ends of the distribution. So they're not on the x-axis exactly, they're up higher because there's actually values there. The tails will be fatter and the peak may be fatter. Sorry, maybe higher, use the wrong word. And this is because the density or area from the shoulders must be moved to maintain the same mean and standard deviation. Which makes the kurtosis value greater than 3. So the excess kurtosis right, which is the kurtosis -3, will be a positive number. All right. If the data has the same mean as standard deviation, sorry, if the data has the same mean and standard deviation, but the data near the mean and from the tails is pulled more toward the shoulders. This is the green curve above. The kurtosis value will be less than 3. So what Excel will give you a negative value. So then the last thing I want to talk about is what Excel functions you use to get this. So in Excel, we're going to use the data analysis packet, and I'll give you an example next class where we go to descriptive statistics. and we're going to get summary statistics. Or if you just want the kurtosis, you can use Kurt and put the data range. Okay. All right, so that is all we're going to have time to talk about today. On Thursday, we will pick up on this very important other topic of association, where we start talking about our two variables related. So thank you for your attention today. If you can, please put your name in the chat before you check out. And I hope you have a great rest of your day.
Thank you. Have a good day.
Thank you. You too.
Thank you very much, guys.
Thank you.
Bye.
Can you post this document on Brightspace?
Yes,
Thank you so much. Have a nice day.
you too.